Hello friends, welcome back to my channel. This is Chandu Prashant. Today I am going to discuss about one of the interesting topic, that is neuromorphic computing, which is also called neuromorphic engineering. Neuro, which is something related to brain, right? So that's why I had inserted the images of brain here. What is the specialty about neuromorphic computing or neuromorphic engineering? So let's see first. These are the contents I will going to cover in this video. Those are introduction, architecture and building blocks, and applications of neuromorphic computing, and already existing neuromorphic research chips. How to construct neuromorphic research chips? What are the components present in these neuromorphic chips? All I am going to cover in this video. Fine. Introduction. Neuromorphic computing, which is a concept developed by Caver Mead in late 1980s. In neuromorphic computing, you basically take inspiration from the principles of the human brain and try to mimic, and mimic means copy, and try to copy those on the hardware utilizing knowledge from nano electronics and a very large scale integration, that is VLSI. Fine. So that means simply remember guys, neuromorphic computing means which is a kind of a architecture, which is a kind of a concept which exactly work like a human brain. That's it, as simple as. Neuromorphic computing refers to computing structures and algorithms that were inspired by the biological nervous system, and currently it is used in wide variety of applications like cognition tasks, decision making and forecasting. So neuromorphic architectures. If we use neuromorphic architectures or neuromorphic concepts, what will happen? It will produce low energy. So it will create less delays. It will increase enhanced computations. Like these are so many advantages are there if we use neuromorphic computing. So these kind of chips are already present in some products as well. If you look at Apple's latest iPhone, they have a chip called M1, which is an artificial intelligence processor, which is not a neuromorphic processor. So that means this concept is not new. This is not something that is far off into the future. Right? Why neuromorphic computing? What is the specialty of neuromorphic computing? Why we have to use neuromorphic computing only? So most of the advanced machines that you see now are using CPUs and GPUs. For high-speed applications, generally we prefer to use GPUs rather than CPUs. Why? Because CPU needs more memory compared to GPU, and the speed of CPU are also less when compared to GPU. Means here GPU means graphics processing unit. CPU means central processing unit. So let's say observe the architectures of CPU and the GPU carefully. Here the memory and the processing unit are two different elements, are two separate elements, are two separate entities, CPU and GPU. So every time you must process data, you send data back and forth between these two units. The transmission of data takes a lot of energy, consumes a lot of energy, and it will create delays. That means every time the CPU fetches the data from the memory, the CPU processes the data, and again it will going to store into the memory. So this is what time taking process. So it will create some kind of delay, and it will produce some energy, and it will dissipate some kind of energy, which is not preferable. So that's why we are using neuromorphic computing concept here. So let's see what is the specialty of neuromorphic computing architecture. So it is a concept which exactly works like a human brain. The efficient processing engine, that is a human brain. So in our brain, processing unit, memory unit are not two separate entities like that. So like here, in our brain, both memory unit as well as processing unit are co-located. They also are not two separate entities in our brain. This is the same concept, or this is the same architecture we are using in neuromorphic computing also. In neuromorphic computing also, So this memory unit and processing unit are not two different entities. They are located or those are merged. Fine. So for example, if here I am going to give a simple example. If you encounter different types of smells in your surroundings, but you are able to identify which is coming from which place, that is the specialty of the human brain. So that's why we are implementing the human brain architecture in neuromorphic computing. So let's see, generally we are using most of the advanced machines using one architecture. I have known about it. So I had already discussed it. Here the memory unit and processing unit are two separate entities. But whereas in case of a neuromorphic architecture, the memory unit and the computing unit are, that means memory unit and processing unit are co-located. It means here the synapse, that means memory, and that here the soma, which means the computing element, here both are co-located. They are merged in neuromorphic architecture. That is the specialty of neuromorphic architecture, which resembles like the human brain architecture. So which avoids the bottleneck between the computing and the memory if you use neuromorphic architecture. Fine. So let's see the interconnectivity or observe the interconnectivity in conventional circuits versus neuromorphic circuits. In conventional circuits, generally we are using resistors, simple resistors, capacitors, inductors, transistors to connect the circuits. But if you wanted to implement neuromorphic architecture, we have to build this type of complex structure. That means which is a neuron, which is a basic fundamental unit of your brain. We have to build this type of structure. Okay. So the basic fundamental unit of your brain is neuron. The neurons consists of different parts like dendrites, soma, axon, synapses, like that. So before understanding the architecture of neuromorphic computing, a neuromorphic concept, let's see what are the parts present in the neuron. If you want to understand neuromorphic computing concept clearly, you should be familiar with how neuron works. What are the parts are there in neuron? You should be familiar with those terms. So here the first part of neuron is the fundamental unit of brain, that is dendrites. These are dendrites means like this. Here the tree-like projections. Next one soma. It is also called somata, which contains genetic information, maintains the neuron structure, and provides energy to drive activities. So next one axon, which is just like a nerve fiber, which can carries the nerve impulses. And next one is a synapses. So it is refers to the point of contact between the two neurons. So observe here, it is one neuron, it is another neuron. It is synapse is the point of contact between the two neurons. That means it will connect two neurons. That's the specialty of synapse. So these are the parts present in the neuron. So we have to build this kind of complex architecture. Like see here, the building blocks of neuromorphic system. So we had known about the basic building blocks of neuron. So let's see the building blocks of our architecture. That is proposed architecture is neuromorphic system. What are the building blocks required to construct neuromorphic architecture? Generally, resistors, inductors, capacitor are not at all used to build this type of architecture. So we are using something new called a memory step. We are using M transistors, ferroelectric FETs, flash memories, and 3D CMOS structures like that. We are using some new concepts or new blocks. The first one is memory star. So memory star, which resembles the functions of synapse, which is already present in a neuron. So the memory star, which resembles like the functionality of the synapse. That means a memory star to design electronic circuits, passive elements like capacitors, resistors, or inductors are used. But a fourth fundamental element is also there. That is called memory star. So it is a symbol of memory star. Going to give a brief idea about what is memory star. So memory stars are important. Why? Because they retain memory without power and non-volatile. It is a simply two-terminal device. The units are same. ohms only. Here mem means they have the memory. Resistor means the normal resistor. That's it. So we are using MEM transistors and ferroelectric FETs also are the basic building blocks of neuromorphic system. If you want to build a neuromorphic chips, memristors, MEM transistors, ferroelectric FETs are used. Instead of resistors, capacitors, inductors and transistors, we are using these components. That's it. So next one, soma. Soma, which is one of the part of a neuron that I had already discussed. So see here. So soma, here a device which consists of a capacitor in parallel with the memristor, which resembles the function of a soma, which is present in the neuron. This type of device provides two important functions. First one is integration and threshold spiking. So if you wanted to resemble or if you wanted to make this type of function, generally we can construct one device which consists of a capacitor in parallel with the memristor. That means if the capacitor is connected in parallel with memristor, so we can get the functionality of sum. So next one is the axon, which is also one of the fundamental element of the neuron. So it's just like if you wanted to, here the long wire resembles the functions of axon. If you use a long wire, it is just similar to axon. That is, it is assumed to provide a circuit connection and a time delay line. Much more research is needed to understand its role and how to construct a device that resembles this function. Still, the research is going on, which suits the functionality of a axon. So next one is a dendrite, which is like tree-like projections. So generally, we are using the 3D CMOS architecture, which resembles the functionality of a dendrites. So pseudo 3D systems have been implemented in multi-layer CMOS-based architectures. So that means if you wanted to construct or if you wanted to build a neuromorphic system, we require some special elements like memristors, MEM transistors, ferroelectric FETs, and 3D architecture, long wires. All these components are required. We are not at all using the normal resistors, capacitors, inductors just like in conventional circuits. We are implementing these kind of circuits. That's why we require these kind of components, these kind of special components. Let's see the applications. In the field of healthcare, you need to get a lot of data from the patients. Fine. For the development of personalized medicine and genome sequencing, etc. While the current sensor technology is efficient in extracting data, fine, but processing it in real time is the bottleneck. So sensors will extract the data, no problem at all, but processing it in real time is the bottleneck. If you use neuromorphic computing or neuromorphic chip architectures here, which would enable processing capabilities within the sensors themselves. Okay, so therefore in the future we may expect significant developments in critical fields like personalized medicine, genome sequencing, etc. That means if you use neuromorphic computing or neuromorphic engineering or neuromorphic kinds of chips, so it will enable the processing capabilities within the sensors themselves. Okay. So next one, drones. And the next application is drones or warfare systems. So generally, camera captures good quality images, but extracting information from the images in real time is the bottleneck. Drones are connected to Wi-Fi and send images to the base station. Fine. But the base station processes the data and sends the signal back. This is a power hungry process. So it will create delays. So and can be intercepted too. If the drone itself has the capacity to process the data, how it will be? It can take immediate action. This can be implemented by using neuromorphic computing. If we use neuromorphic chips here, the drone have the capability to process the data by itself. That is the specialty of neuromorphic computing. So next one, space applications. Even in space also, rovers captures images and send them back to the Earth station for processing. If an energy efficient processing system is installed there, we will have Mars rovers and Moon rovers driving on their own. So this energy efficient system is nothing but neuromorphic computing. If you use neuromorphic computing type structures here, the Mars rovers and Moon rovers driving on their own. So it will create very less delays. There is no need to send back to the Earth station for processing. They only process itself. That's the specialty of neuromorphic computing. So other applications. Also, we use all sorts of applications like Alexa, Siri, etc. But they don't work without Wi-Fi. The main problem with these systems is that their processing power is limited. Fine. Whenever we give them any input, they just transfer it to the server where the processing happens. The output comes from the server to the device and device simply gives the output. So see here, it is all like a time consuming process. So here, that means here the memory and the processing unit are two different entities. That's why all these processes will going to take place. So if you use neuromorphic computing architecture, neuromorphic chip here, what will happen? In such scenario, we not only make this device compute independently, but also reduce cloud dependence. If you use neuromorphic computing architecture, we can make this device compute independently. But instead of this, we can also reduce the cloud dependence. We can avoid the cloud dependence also. If we use neuromorphic computing architecture, generally cloud dependence is a major source of security vulnerabilities and adversary attacks, which can avoid by using neuromorphic computing. So generally, these applications like autonomous vehicles and robots, generally these are power hungry devices. If you use a neuromorphic computing or a neuromorphic chips in autonomous vehicles and robots, it will going to consume very less power. So within a less time, we are going to get our required applications. So these are the applications. So existing neuromorphic research chips. So generally, we have different kinds of neuromorphic research chips available. In India also, some of the startups are presently working on SRAM-based neuromorphic computing chips. So let's see the IBM TrueNorth chip, which is a existing neuromorphic research chip, which was developed by the IBM. So that is IBM TrueNorth chip. So it is IBM TrueNorth chip. So it is the internal structure. Here the processing unit and memory are merged together. Those are not two different entities in this processor. So these are memory unit and then processing unit are co-located here. So in IBM TrueNorth chip. So which is just functions like a human brain. Already I have discussed. Neuromorphic chip means function like a human brain. That's it. As simple as. IBM research namely a biologically inspired chip TrueNorth that implements 1 million spiking neurons and 256 million synapses on a chip with 5.5 billion transistors with a typical power draw of 70 milliwatts. So it consists of 5.5 billion transistors. This IBM TrueNorth chip consists. So next neuromorphic research chip is the Intel's Loihi chip. A neuromorphic research test chip designed by the Intel is Intel's Loihi chip. So it uses an asynchronous spiking neural network to implement adaptive self-modifying event-driven fine-grained parallel computations used to implement learning and inference with high efficiency. So Intel's Loihi chip also there, which is a neuromorphic research chip, which is proposed by the Intel. Same is Intel Loihi chip. So it consists of a 128 neuromorphic cores, many core IC fabricated on Intel's 14 nanometer process. So it is a Intel's Loihi processor, which is a Intel's neuromorphic research chip. So it is a board, which is a Intel board, so which consists of around 8 to 32 neuromorphic research chips. So these are the existing neuromorphic research chips. So simply guys, it just works like a human brain. So in order to overcome all these disadvantages. Fine. Thank you. I hope you have enjoyed this session.